Welcome to this presentation on psychrometric applications, looking at cooling towers specifically. We've looked at some air conditioning, dehumidification, humidification processes. So this one's another one with cooling towers because we've looked at power generation systems, and we're going to go in more depth in this, but that's what I want to highlight with as we're looking at to start off here. So we're at the end of things here. We're down here with the applications piece of psychrometrics. So we've gone through all this stuff here this semester. So good work, folks. So we're just finishing up here as we look at where we're at in the whole scheme of things. So going back to the power systems, vapor power systems, right? We have this cooling tower over here. And we've basically with the psychrometrics piece, how do we get this cooling that happens? Because what we're trying to do here is after we come out of the turbine, we want to go through this condenser to take whatever kind of vapor we might have left and get it all the way over to a saturated liquid, if not subcooled regime. And to do that, we need to have this cooling water coming through here. And obviously it's going to go through here, get warmed up, so we have the warm water coming back. So what happens in this process here, that we get the cooling. So you can imagine if we're spraying this, we're going to get some evaporation. So we're going to have some loss out the top here. Cooling water, probably some makeup water because we're going to lose some stuff out here. So we got to make it up somewhere. All right, but this is what we're going to be looking at the cooling tower. All right, so here's the cooling tower, looking at a little bit more closely, kind of our engineering model. All right, so we have the warm water that's coming back from the condenser. It's coming in at some temperature and some mass flow rate. It looks like the dot got a little messed up there. All right, but it's coming in here, it gets sprayed in here because we want to help to ease the evaporation process. So when we got droplets, it's going to have a lot more surface area. So it'll be easier for it to evaporate there. The atmospheric air is coming in here, so we have some moist air with some relative humidity, or humidity ratio and some relative humidity. But that's coming in, and as long as this relative humidity that would be coming in is less than 100%, we'll evaporate some, and we'll go out the top with some moist air. With here, our omega-4, the omega at state 4, the humidity ratio is going to be higher because we're going to have more moisture. Same amount of air. That's the only place the air is coming in, dry air. This is the only place that dry air is going out. So the humidity ratio will go up. It'll be greater at state 4 than it will be at state 3. But mass flow rate of air will be constant. All right, some of it won't evaporate and we'll end up with liquid down here. And we might have some makeup water. So some of the problems we'll be looking at will include some makeup water. Some of it we'll ignore that. And then we'll have the return water coming back. All right, you can see here at T2, this whole purpose of this process, T2 is less than T1. Right, so T1 is the warm water coming in, so we have a cooler water now going back to the condenser in the vapor power process. All right. So where does this happen? Where do we see especially this air come in to the cooling tower? That's what I want to show you in the next slide. All right, so here's some pictures of our cooling tower. So we're used to seeing, right, this overall image, right, the curved surfaces here. All right, and this, interestingly, it's the kind of the image for the nuclear power industry, but yet there's no nuclear processes going on here. It's just the water that's being evaporated off in the cooling process. But what you see here, right down here at the bottom, there's this open space, and a little bit more zoomed in here, kind of the side view. Obviously, the picture is more focusing here on the actual nuclear plant. But what I want to show here, this is where we have that air coming in. It's kind of being drawn in as the moisture and evaporation goes out the top. The air is going to be drawn in, right? Conservation of mass is going to draw in the air there. And so that's that drier moist air that picks up, evaporates our vapor, our mist. Actually, I guess we usually spray it in, ultimately cooling the water before it goes back in to the process here. So that's what we're going to analyze today in our example.